initial, Q final e depende de t. Mas se você fixa as coordenadas é uma função de t. Tá? E agora você pode ver isso primeiro com um exercício assim, puramente matemático. Se isso é uma função de t, pode ser ou não, mas vamos agora assumir que não vai fazer problemas se eu penso desse t não só no acho real, mas no complex plane. Tem problemas com isso, mas a gente vai discutir isso. O que a gente ganha disso? Se você pensa dessa forma, você poderia falar, então, vamos pensar de um objeto, sei lá, Q initial, Q final, e chamar uma variável z, que a gente coloca aqui, e estudar esse objeto, onde z pode ser real ou imaginário. Se fosse real, vai aparecer a ação que a gente conhece da Classical Mechanics. Se a gente usa z como puramente imaginário, se z é puramente imaginário, vai aparecer a ação da Classical Mechanics. Se z é puramente real, se você vai pela construção, vai aparecer esse objeto, que também parece com uma ação. Tem aqui o menos, tem um signo diferente, você pode entender toda essa estrutura simplesmente pensando, isso é uma integral sobre o purely imaginary axis, 0 a, sei lá, o valor que você está interessado. Então, pela substituição. Por que a gente iria fazer uma coisa assim? Isso é simplesmente que, vocês devem também já ter experiência. De vez em quando a gente generaliza os objetos, a gente ganha muito. A gente agora, dessa forma, pensa de um objeto morando no complex plane. A gente vai achar um exemplo que é muito mais fácil fazer esse cálculo em alguma outra direção que não seja o purely imaginary ou purely real axis, tá? Pode existir direções que esse cálculo é muito mais fácil. Aí a gente vai chegar numa resposta que depende desse z, dependendo se a gente integrou aqui de 0 a t, ou a gente integrou 0 a beta, ou a gente integrou a qualquer coisa, vai depender desse valor. Agora, a única pergunta que a gente tem que saber, faz sentido? A gente vai sofrer um problema de analiticamente continuar essa função, por exemplo, no acho puramente imaginário real para chegar no propagador da mecânica quântica ou da estatística, tá? Então a gente tem aqui um objeto que é o master propagator, que permite, se a gente faz uma análise da estrutura assim no faz complexo, permite depois de ter feito o cálculo, fazer a extensão analítica para um regime que nos interessa. O que a gente ganhou foi que o cálculo em certa direção pode ser muito mais fácil do que em outra direção. Tá? Então a gente pode estudar esse objeto em princípio e sempre vai ter um passo que a gente tem que ter cuidado se a gente pode depois continuar analiticamente para onde a gente quer, ou se tem algum cut, ou se tem algum polo que a gente não pode. Tá? Então isso é o único problema. Mas o conceito de geralizar times complexos é muito powerful, porque se generaliza o objeto e tem contas que é mais fácil fazer em certa direção. A gente vai discutir um exemplo disso depois, tá? Então, você pode primeiro ver isso como simplesmente uma coisa matemática. Você generaliza para o complex plane e depois vê se tem a estação analítica. Se a gente faz isso aqui, a gente está falando de partition function é igual a uma integral sobre periodic path, que tem um weight, que agora é exponential suppression of a kind of action in imaginary time, which differs here by the sign, and we can already extract from this a lot of physical intuition, okay? So now we see here, that's a discussion, that the kinetic term here tells you that, well, if beta is small, okay, if we are in the high temperature limit, we cannot travel very far, because if you just think, well, if you want to travel far in a short time, you need a high kinetic energy. This will be suppressed, okay? So there is some physics to this that we now want to see in one specific case. So first you can think of it as a completely like mathematical like thing, and you can do it. But the nice thing is that there's also physics in it, okay? And this is like trying to, like one way to see it is how the classical partition function emerges from this, which we say, so this answers the question in terms of path integrals, what is the canonical partition function of a single particle quantum mechanical system? Well, it's given by this expression. So let's see what is the consequence of this. Okay, or questions or okay. So then, given this observation, we see that, well, the typical distance a particle travels in space depends well on the mass and on the time, on the temperature, no? Because you want to have small kinetic energies. So let's just make a very simple estimate. Distance traveled depends on mass and temperature. So you're studying like periodic paths. So this is like coordinate space. This is at time 0. You start at some point at imaginary time beta. You should come back to the point. And we're just interested, what is the typical distance a particle with a given mass travels within the time set by beta, okay? And just do a very simple estimate, which is the following. So let's write down the kinetic energy. Let's say that the potential, of course, will influence this, but let's say the potential is more or less constant. We will later see when this is consistent or not. Then the entire weight is given by this kinetic term, okay? So this is then describing kind of a free particle. So if we think about, well, what this gives, well, this is like the velocity integrated over time. So this will be given by the velocity when you travel. So if you want to travel distance d, well, you need to have like a velocity to return. So if you travel a distance d in time beta, then the velocity is of order d beta squared, h beta, and you integrate this over time, you have h beta. Okay, so just a very simple estimate of the kinetic energy. If we see this, so what cancels out is what? So we get d squared over h beta, and let's put in the temperature because somehow I think it's better temperature. So we see that the typical distance, well, it should, so this should be of order smaller than 1, because if this is like larger than 1, then this will be exponentially suppressed. Okay? Well, this is just a very simple estimate. Now, if we then insert this into the action, we get still a factor 1 over 2n. Oh, well, this is a typical action, so I should write. And now, what this means is that d squared t over h 2m h bar, this should be smaller than 1. Okay? This is what we get once we have estimated the kinetic expression like this. This we get from saying that this should be not larger than 1. Okay? So what we get from this is that the typical distance is smaller than 2m h bar divided by t. I forgot an 1 over h bar here, so there should be an h bar squared. Okay? So this would be the typical distance we get a particle travels if we make a very simple estimate and say, well, how far can it travel such that the kinetic energy, or the kinetic energy part of the action is smaller than h bar. Taking the typical distance, we arrive at this answer here. Okay? So we see first of all, well, if temperature becomes very slow, so if we go to the quantum limit in a way, then we can travel quite far. However, at high temperatures, we expect somehow the classical word to emerge, then we see that, well, the distance becomes small. Okay? But now we can even take a closer look, and so does someone recognize what this is? Well, this is just the thermal wavelengths of the particle, no? So you have a given temperature T, and then you say, well, the thermal wavelengths is, you say you have some kinetic energy, this defines the thermal wavelengths, and this is exactly what this is given by this, okay? So this distance, the typical time depends on nt, and actually the typical distance is of the order of the thermal wavelengths, which is given by h4 squared over t. Okay? This is just a very simple estimate. But this is quite nice because this tells us that, like here we are talking about, in a way, sum over path, which is all classical, okay? But we see now what the quantum fluctuations actually mean. So we know that, well, the particle is not really a point-light particle in quantum mechanics, and we see that in the quantum partition function means that you can, the point-light particle, if you still want to think about path, you can understand it as a point-light particle traveling in imaginary time over a typical distance set by the thermal wavelengths. Okay? So that's, I think, quite a nice different way to look at this. So it's typical. Can I erase this? So the typical distance depends on mt, and it's actually given by the thermal wavelengths of particle. So this then also tells us that, again, if we go to the high temperature limit, somehow the classical world should emerge. If we go to large masses, also the classical world should emerge. So let's see how we get this now from the path integral. So let's start out from this partition function and see in what limit do we arrive at the classical partition function. So let's do this here. So let's start out from the integral, the partition function given as the sum of all these periodic paths, where here we use the path integral representation. Now, the path integral, again, depends on two contributions. So we have here the potential and we have the kinetic term. Now we have here made a simple estimate which says that, well, the typical distance the particle travels is limited by the thermal wavelengths. Now we can look at one limiting case, which is that here this potential actually does not vary on the scale given by the thermal wavelengths. Okay, so if we think of some smooth potential, then we have to say smooth on what scale? Let's say smooth on the scale set by the thermal wavelengths. So if this is the case, how can we simplify this expression? Well, if this Q is restricted to radii limited by the thermal wavelengths, and this is a constant function on the scale, we can just pull out this, because this becomes independent on the path, it just depends on the coordinate Q. Because the way you travel, it's all the same. Okay, the potential. So let's pull out this here to see what we arrive at. So this should be a fine approximation if we assume that the potential does not vary on scale set by the thermal wavelengths. So what we arrive at, we can pull out the potential here and arrive at just an integral now over fluctuations which contain the kinetic part. Okay, so in this case we can write z. Let's call this okay, still z. This is under this approximation. We arrive at e to the minus no, let's first do it simpler and look at this element here, which still depends on q, okay? Just this transition element. In the end, for the partition function, we should integrate over all q. So we can pull out just the potential evaluated at q under this assumption, and then we still have the integral over fluctuations. Which are now given by e to the minus beta h bar m half q dot prime squared. Okay? So this is just again the propagator for the free particle, however now in imaginary time. Okay? So we have done this integral where does this come from? This comes from such a transition element where here we substitute p squared over 2m. Okay? So we did this calculation. To m h bar it. And let me just write down the result that we had. That was m over 2 pi t h bar. Okay? So this is the result that we had for this free particle propagator. Okay? Evaluated at the same points. Okay? Now, what we here consider is the problem e minus beta p squared over 2m cubed. Okay? Just the same problem where now beta is instead of it. And now comes exactly what I have said in the beginning. So why don't we think of this as e to the minus p squared 2m h bar times some variable that we call d. Okay? So we can substitute it over h bar by some z. We have done the calculation for the specific value z equals it over h bar. Now let's see if we can make an analytic continuation. So we have a square root, we have some cut. This is like the square root of the logarithm at some negative axis. Okay? So we have done this integral, this function, let's call it, let's introduce a function. Okay, if it's getting too confused, just tell me. We can introduce some function f of z, defined as q e minus p squared over 2m times z. Okay? So this would correspond then, if we just take this value, 2p z over h bar, I guess. So we have done this for the specific value z equals it over h bar. It over h bar. Sorry, h bar squared should be the other way around. Okay? So we have done, and now we can ask, well, for what z's is it allowed? So we have done the evaluation for z being it over h bar. But we see that this is completely analytic, this function, if we don't care about, let's say, the cut. So if we don't cross the cut of the logarithm, this is completely fine. So we can think of d, instead of living on the real axis, we can analytically continue to all the values here if we don't cross this cut. Okay? So all we need to do is to evaluate this, is to generalize this function, this general function, now to values d being beta. Okay? And this is, if we do this, we get this result here, okay, for this expression. So if we do this, we arrive at e to the okay, let me if we do this, we get again some square root. Well, the I disappears. We get an h bar squared. Here comes the temperature. So we just have to substitute here the T. So we actually immediately get again the thermal wavelengths. Okay, so this gives the thermal wavelengths. So if we do then the final integral over Q, we get the partition function. Then we just write down the result for the partition function. Clear? Just to make it not too. So if we do so, we get for the partition function mt over 2ph bar squared. Thermal wavelengths, then we have the integral of the coordinate e to the minus q temperature or times beta. Okay, because we integrate this over q. Well, and this you see is just the classical partition function. Okay, so this is like a classical partition function, and the only question now we have to ask, if the classical limit is allowed, is what kind of potential do we have, on what scale does it vary, and how does this scale compare to the thermal wavelength of the particle? Okay? And just, let me see, just to make it into some more like real. So the typical distance is a particle with temperature m, with mass m and temperature mass m and t temperature travels is given by the thermal wavelengths, and for a hydrogen atom, at 1 Kelvin, for example, if you put in the number, you will find that the typical distance is of the order of 10 angstrom. Okay. Now, what else do I have? Okay, so if you take oxygen, then you find that the typical distance is of the order of 2.5 angstrom. Okay, and actually, well, what you see, well, this says like 1 proton. This says like 16. So square root of 16 is a factor of 4 difference. No, so this would be oxygen at 1 Kelvin. 1 Kelvin, and at 100 Kelvin, well, it should go with a factor, square root of T, so 100, so you get E being 2.25. Okay? So you see, when you increase, like what you expect, if you increase the mass or if you increase the temperature, then you should actually travel to lower distances, meaning that if your potential then doesn't vary on this scale, then you can do your classical analysis. Okay, so this is. Honestly, I don't recall like how this is discussed in statistical mechanics, but I just looked into Feynman yesterday and saw this. It's like nicely described in Feynman's book, and I think it's just. It's really nice. No, it's very beautiful. No, so you have like. The Cont partition function allows for traveling in imaginary time, the typical scale set by the thermal wavelengths, and you immediately see how classical mechanics arrives if you're considering in a way a point particle, meaning that the potential cannot resolve any structure. So the potential is constant on the thermal wavelengths of the particle. So it's I think very nice. So you see that we will see an example where this imaginary times allow for a calculation which cannot be done so easy if you don't allow for imaginary times, which is a mathematical trick in a way. But here you also see that it's really nice physics. Now, what I still would like to do, but como é que é? Podemos fazer mais 15 minutos ou chega ou vocês têm coisas para fazer, está com fome, ou a gente pode continuar com 15 minutos? Para mim os dois está bom, só tem que ir. Porque, eu vou só falar, porque agora a gente poderia fazer ainda, calcular simplesmente a density matrix elements para o oscilador harmônico. Então a gente calculou em real time, é só substituir imaginary time e ver se o resultado faz sentido, mas é um pouquinho, iria levar 15 minutos. Podemos fazer na próxima vez ou agora. Para mim, tanto faz. Tem que decidir. Bom, decidem vocês e me falam.
Você pode fazer no que tiver que sair, sai depois.
Vocês decidem. Vocês, eu quero que vocês tomem responsabilidade.
Está gravando? Eu vou sair para comer, mas eu tenho uma coisa.
Olha, é simplesmente assim, eu nunca sei quanto a informação é nova e quanto não. Então vocês já estão com muita coisa na informação na cabeça, eu falo, não, foi tranquilo, vamos fazer mais uma coisa. Iria fechar um assunto. Se vocês falam, não, já foi muita coisa, a gente vai fazer na outra vez uma revisão e fazer esses exemplos. Mas se já foi tudo claro, não tem que na próxima vez revisar e fazer esses exemplos, porque aí vocês vão ficar, não está acontecendo nada aqui. Eu não sei se é rápido, lento, eu preciso de feedback. Pode falar aberto assim, não?
Por mim, você pode continuar fazendo, eu vou sair, mas eu vejo o finzinho depois gravado.
Tá, e o resto? Tá, chega, querem mais?
Tranquilo também.
Tranquilo?
Eu só tô com fome.
Então, votação.
Eu só vou sair porque eu tô com fome, mas por mim continua.
Tá. Então, quem vai sair? Quem vai sair? 1, 2, 3, 4. Tá bom, então vamos deixar para a próxima.
O problema